let's solve this physics problem. So this one's a little bit different, and I saw it in a book, and I thought I'd solve it because it's just different. So you have a mass. There's a table there too. I didn't draw the table. There's a 6 kilogram mass on a frictionless table, and then there's two masses connected to it over pulleys. And the question is, what's the acceleration, and what's the tension in the two strings, or the two separate strings? Okay, so this looks like a classic half Atwood machine. So the half Atwood machine has a mast right here, and it has a pulley. Oops, that's a bad pulley, with another mast over there. Okay, that's actually that's a great problem in a lot of different ways. This one's a bit more complicated. I'm going to solve it in the traditional way, and then I'll show you a trick to solve it, and hopefully we get the same answer both ways. And if not, I'll either delete the video and you'll never know, or I'll just post it anyway, and someone will say in the comments down below, hey, you made a mistake. Yeah, I know. Okay, well, let's get to it. So this is a 1 kilogram mass, 6 kilogram mass, and 3 kilogram mass, but I'm just going to call them M1, 2, and 3 just for now, so we don't have to worry about things. Let's go ahead and just start drawing free body diagrams. And I'm going to start with this first mass right here. So here's my mass, M1. I know I have a downward gravitational force, M1G, and then an upward tension force, I'll call that T1. So this is T1 pulling that way on this mass, and that way we'll call that T2. Okay, so that's my mass. I've probably told you this before, but in the half Atwood machine problem, I remember being an undergraduate student and making the mistake of saying the tension is equal to the weight. And it looks like it should be, but it's not, because that would be true if it was accelerating. But it's not if it was stationary, but it is accelerating, so it's not true. Instead, I have the following equation. F net in the y direction is going to be equal to T1 minus M1G, and that's going to be equal to the mass times acceleration for that system. Let's assume, and it makes sense, that the whole thing accelerates this way. So that's going to accelerate in the positive y direction, so it's M1A. That's important. Put a box around it. That's an A. Okay, I don't know T1. I don't know A. So I have two things I don't know. I can't solve that equation. Well, let's go ahead and look at that block right there. That one's a little bit more complicated because we do have a gravitational force M2G. I do have a normal force, and then I have T2, and then I have T1. Now, I don't know the normal force. I do know the gravity. I could find the normal force, but I just don't care, right? Because there's no motion in the y direction. I don't really care about that. But in the x direction, I can say F net in the x direction is going to be T2 minus T1, and that's going to be the mass times acceleration. So this is mass M2 times A. Now, I'm assuming it accelerates in the positive direction. So that's a positive. Maybe I should put a box around that. That seems like an important equation. I think that it is. Box. Now let's look at that third mass right here. I'll put it right. I want to put the equation right there. I'll draw it up here. So here's my mass. I have the downward gravitational force M3G, M3G, and then the upward tension T2. Now for this one, F net y is going to be T2 minus M3G. Now that one's going to accelerate in the negative y direction, right? Because if that's accelerating up, that has to accelerate down. Fixing my microphone there. Okay, so this is going to be negative M3A. Let's put a box around that. That's an A. Why do I keep doing that? A. Okay. 1, 2, 3. 1, 2, 3. 3 variables. 3 equations. So that's math time there, right? Okay. So I think I'm going to try to do it in this extra space over there, and then I'll erase stuff as I need it. So the question is, which should we solve for? We want to solve for everything. You've got to make a choice here. This one looks pretty easy to solve for T1. So I'm going to go ahead and do that. Let's solve that for T1. And I can just add M1G to both sides. So T1 is going to be equal, let's put that up higher. I need all the space I can get. T1 is going to be equal to M1A plus m1g. Now, you might say, hey, factor out the m1. That'd be cool. But don't do that, because you're just going to have to undo what you did, because we're going to need to get a1 by itself. But now I have t1 by itself. I can plug that in down here, right? So let's plug that in down here for t2. So I get t2 minus t1, which is going to be minus m1a minus m1g, right, because that's t1, is equal to m2a. Now I can solve this for t2. So let's solve this for t2 by adding that stuff to the other side. t2 equals m2a plus m1a plus m1g. And so I can factor that out. t2 is going to be equal to a times m1 plus m2. So you notice there I factored out the a because that's the variable that I want, plus m1g. Now down here, I'm going to substitute in this expression for that t, and I'll have an expression that only has a in there. So I get a m1 plus m2 plus m1g equals, no, that's that. And they have to subtract minus m3g. Now that one, I don't care about g, that's constant. And that's equal to negative m3a. Ooh, just barely ran ahead of the room. Okay, so let's add m3a to both sides and subtract that from both sides. So I get a times m1 plus m2, and then I have a plus m3, equals, and that I moved to the other side, so it's going to be m3 minus m1 times g. And that's the right answer, I can tell. So now I'm going to solve this for a. A is equal to m1, no, that. It's going to be equal to m3 minus m1g, all of that over m1 plus m2 plus m3. So let's just check some stuff, right? We have an expression. We can check some reasonableness of this. Number one, does it have the correct units? So this should have units of acceleration. Well, here I have a mass times acceleration divided by a mass. So it does indeed have units of acceleration. That's good. Okay. Now, what about what cases could we look at that would be like special? Well, up here, what if m1 is equal to m3? In that case, what would the acceleration be? The acceleration should be 0, right? You have equal masses on the sides. It's not going to go anywhere. So if m1 is equal to m3, it goes away. What if m1 is greater than m3? Well, in that case, it should accelerate the opposite way. I should get a negative value. I do. Okay, what else could we do? Well, we could do, what if m1 is 0? And then I do get the half Atwood equation, which I'm not going to derive that for you, but that is indeed the case. What if m1 and m2 are 0? Then this is just all by itself. It should have free fall acceleration. So if m1 is 0 and m2 is 0, then I get m3g over m3, so I get g. So I think it's a pretty good equation. Okay. Now, once I find that, I can go back up here and find t2. I don't need to do an expression for it. I'll get a numerical value for it. And then once I have t2 and a, I can go up here and find t1. So I kind of like work backwards. Let me show you how to get this in a different way. And then I was going to put this in Python with a calculator, but I don't really want to. I don't think there's any point in that, right? I just want to show you the other thing. And then I will dismiss you for the day. Okay. So there's a trick to get this equation. I don't like tricks. I like this way better. But I'm going to show you the trick. And it's useful to think about. Okay, imagine this system that can only move in the S direction. Okay, because that one's moving that way, that one's moving that way, and that one's moving that way. And I think of my system as m1 plus m2 plus m3. The whole thing is my system. Well, if that's the case, I could kind of draw it like this. I'll call that capital M, and then I have a gravitational force pulling on this side, so it'd be M3G, and then I have a gravitational force pulling this way, M1G. So my F net on the system, I don't need to worry about the tensions because they're part of my system. F net in the S direction technically would be M3G minus M1G, and that would be equal to the total mass times acceleration. So if I just put in the total mass and solve for A, I get A equals M3 minus M1 G, that's the force, divided by the mass, M1 plus M2 plus M3. Oh, look, it's the same thing. And then you could use that once you know the acceleration. It's pretty easy to find T2 and then T1 and then find, well, you don't, that's it. You don't even need the middle mass after that. It matters, right, because it's right there. Oh, another check. If M2 is 0, you have an Atwood machine. Okay, assuming massless pulleys. There you go. It was a fun problem, don't you think? I enjoyed it. The end.